it work?
Yeah. Please, John, get everybody to come in if they're in the door. Thank you, everyone. Hope you all enjoyed those delicious treats out there. The coffee was also pretty good. And Nigel doesn't seem to concord. Well, I don't know. Not every hotel conference experience had a decent coffee. All right, so we're just going to get started right on time. You have reminding the speakers that it's 25 minutes plus a few minutes questions. So please, Jannik.
Okay, thank you. Hello, everyone. So the topic of this talk will be blind zkSNARKs. Is it okay to go? Yeah, okay. Blind zkSNARKs. They are a cryptographic primitive that you get from combining zkSNARKs with fully homomorphic encryption or homomorphic encryption. And I will also be talking about two applications, which is private proof delegation and verifiable computation over encrypted data. So I'll start by introducing the second setting and to give an introduction into this research domain. So, okay, it works. So the setting is you have a client and a server. The client has a low amount of computational resources, and he's outsourcing some computation to a server. And there's an input U. There might be a server input W. Is computing a function f and returning the output, right? So here you can say, what if the server is dishonest? And we can try to remove this trust assumption using something you're all very familiar with zk proofs. So you force the server to actually provide you with a proof that the client can verify, right? But one thing you don't have here is that the server can be curious about this input U and the output, and this might leak some privacy. So there might be another cryptographic primitive we can use to prevent this, right? So yeah, in general, we call this verifiable computation, right? Okay, so quick intermezzo. I think most of you are familiar. So you have homomorphic encryption, just a normal encryption scheme, except that it's homomorphic for addition, for multiplication. We don't actually require it to be fully homomorphic here for this application, but I might just use the term FHE interchangeably. So in general, homomorphic encryption can transform some arithmetic circuit, for example, this computation F, into an homomorphic circuit, which I'll denote by eval F. And it has this correctness property, meaning that if you choose the ciphertext space parameters large enough compared to your computation, then you have this homomorphic property. And yeah, for this talk, the FHE scheme can just be symmetric. So encryption and decryption is using the secret key. So using FHE, we can remove another trust assumption. So the client instead sends a ciphertext of its input, and then the server homomorphically evaluates the function, or blindly evaluates the function, and then returns a ciphertext of the output, which the client can decrypt. But here you don't have this integrity, right? So we'll refer to this as computation over encrypted data. A natural question is, can we have both these properties at the same time and be secure against a dishonest and a curious server, right? So is it possible to send over a ciphertext, have the server homomorphically evaluate the function, but then also provide a proof which the user can verify? And we will refer to this as verifiable computation over encrypted data, or vCoed. And this is a concept that was already introduced by Fiore, Gennaro, and Pastro in 2014. And you can kind of regard it as a cryptographic variant of a trusted execution environment. But you don't have to trust the hardware, right? But as you know, zero-knowledge proofs and FHE are themselves already kind of fairly expensive protocols, so combining them is not necessarily very efficient. But we'll try to make it as efficient as possible. So let's get to the first straightforward way of achieving vCoed is by using verifiable FHE. And in verifiable FHE, you simply take this FHE scheme and you wrap a SNARK or some verifiable computation around it. So you take your function f, you construct a homomorphic circuit, and then you represent that homomorphic circuit in a constraint system that you prove to the client. This is verifiable FHE. But yeah, as you can imagine, this is not very efficient, right? So in the first step, you already have a circuit size blowup because in FHE, you compute these field operations in a large polynomial ring, which you'll have to represent in the constraint system. Secondly, it's not only these ring operations, right? So in FHE, you have noise, and sometimes you have to do maintenance computations to remove this noise or maintain the compactness of the ciphertext. So these maintenance operations have to be performed fairly often, and depending on the FHE scheme, they will either require some rounding or taking a remainder. And in the context of zkSNARKs, this will translate into doing a lot of range proofs, mostly, on these very big polynomial rings. And you know that this is not very efficient, right? So state-of-the-art schemes will either have this function f be very small, like hundreds of operations, or do this for smaller FHE schemes that have a small plain text space. So we can take a look at the opposite approach, right? Because in this previous approach, we are proving the ciphertext space operations, and this is more than we actually want to do. We want to verify the plain text space operations. Right? In some applications, you do actually want to prove ciphertext space operations, and then you really need to use VFHE. But for achieving vCoed, VFHE is kind of overkill. So in 2024 at Crypto, Sanjam Garg and his co-authors proposed this opposite approach, which is to wrap the FHE scheme around the SNARK. So you take this computation F, you make an arithmetic circuit that represents this proving computation for proving that function, and then you evaluate the proving computation homomorphically. And we call this blind zkSNARKs because essentially someone is blindly proving a computation. He knows what the computation is, but he doesn't know on what inputs he is proving the computation. And this only proves the plain text space operations. So take, for example, when f is simply adding the input u and w, then you could compute this in FHE as simply addition of the ciphertext, but of course you can add as many ciphertexts of 0 to this as you want. In VFHE, you will notice this, right? Because you're proving the ciphertext space operations, but in blind zkSNARKs, you can't tell the difference because you're proving plain text space operations. So it's important to distinguish these two. Okay, so how do we use blind zkSNARKs for achieving this vCoed? You have the normal verifier prover setting, but then the client encrypts his input, sends the input to the server homomorphically evaluates the proving operation on ciphertext, and then sends back an encryption of the output and the proof, which will also be encrypted, of course, right? So then the client can decrypt the output, can decrypt the proof, and then verify this proof. Because the proof is encrypted, this scheme is, of course, designated verifier. Only the person that knows the secret key can actually verify the proof. But as I showed in the first slide, blind zkSNARKs have another application, which is private proof delegation. So let's say that the client is actually the prover. As you all know, proving computation can be fairly expensive and might be too expensive for constrained devices. Think, for example, of schemes like zk email, zk P2P, private cryptocurrencies. Blind zkSNARKs can also help here with private proof delegation, but to a single party. Right? So the client encrypts his private input, or maybe even the entire computation trace, and then sends that to a server who homomorphically evaluates the proof, sends back the encrypted ciphertext and output, and then the client can decrypt the proof and decrypt the output. But of course, the scheme was designated verifier, So to actually be useful for private proof delegation, we'll have to make this publicly verifiable. And we show that you can do this by appending a proof of decryption. And you'll see later why. So as a summary, blind zkSNARKs, you can achieve vCoED, private proof delegation, and this vCoED application kind of overlaps with VFHE, but VFHE can achieve more than this and is useful in other applications. So if you're interested in VFHE, I recommend sticking around because there will be a talk about this later. Okay, so how do you make a zkSNARK blind? Normal proof systems, they just prove that a statement and a witness in a relation, but here we kind of prove that some ciphertext, if you were to decrypt them, that their plaintext representation would be in the relation. And we define this new notion of plaintext knowledge soundness, meaning that an extractor that has knowledge of the secret key could extract the witness. And it's also important to notice that if you're outsourcing a computation or the proving to someone else, then that's in a normal proof, the server could add some inputs to this, and by the zero knowledge property, automatically get server privacy. Here, this is not necessarily the case because the FHE scheme might leak some information in the noise, so you might have to use an FHE scheme that has this circuit privacy property. Okay, so how do you construct this blind zkSNARK? Let's start from a normal HIOP. You send some messages, you receive challenges, you're all very familiar with this. And then you can, of course, compile this into a zkSNARK using BCS compilation. Right? So you make a vector commitment of the messages, which produces a root, and then you use kind of via Chamir to generate the challenges. And then in the end, you have to open some of the elements in the vector commitment and do some verification there. So in a blind AIOP, you do something else. So you send the encrypted versions of the messages, because that's the only thing the prover knows in this case. And we show that it's sufficient to actually use these to compute the vector commitment on this ciphertext. So you could also make a blind SNARK by fully homomorphically evaluating these vector commitments, but that would be very inefficient. But it's actually sufficient to just commit to the ciphertext representations. So we show that these blind HIOPs, they inherit this round-by-round plaintext knowledge soundness from the HIOP, and you can still simply apply this BCS compilation with some kind of requirement on the HIOP, which is also always satisfied. So in the designated verifier setting, the client decrypts these values that are opened in the Merkle trees. He checks some identities that which just depend on the HIOP, and then, of course, naturally checks these openings and the via Chamir. And then you can make this proof publicly verifiable by simply appending these decryptions of the plaintext, but then also providing a proof of decryption, basically that these ciphertext correspond to the plaintext you're appending to the proof, so that anyone, even without knowledge of the secret key, can verify the proof. Of course, these proof of decryptions need to be zero knowledge as well, because they cannot reveal the secret key, otherwise you would lose privacy of your witness. So we look at how to construct an efficient blind zkSNARK. So we select an IOP that is fairly linear, which is compatible with the FHE scheme. And then also we need a high precision HE scheme that allows for large plaintext spaces, because the SNARKs are sound because of the size of the plaintext space. So we also need the FHE scheme to be to allow this. But most FHE schemes, they don't like large plaintext spaces because this increases the noise growth. Then also we need to optimize the IOP to actually be as efficient as possible for specifically HE computations instead of plaintext operations. And then in the end, we need to construct a proof of decryption for that specific HE scheme that we're using. So what is the computational interface here? We have the HE scheme, it works over a ciphertext space, but the plaintexts are simply vectors over some finite field, and it has element-wise operations, additions and multiplications, and can also perform permutations. So for those who are not familiar, so FHE schemes allow you to have this SIMD property, so that each ciphertext represents a vector of plain text values, and you can do element-wise operations. And we try to make use of this fact to make the blind SNARK as efficient as possible. Now, of course, there's also noise growth, so we want to decrease or minimize the noise growth as much as possible, because this will increase the ciphertext space parameters that we need to use in the FHE scheme. So in general, this is not very good, and there's not many FHE schemes that are compatible with this. So there was another FHE scheme kind of co-designed with this paper called GBFE, and it's sort of a best of both worlds between normal BGV and BFE, which allow for very large SIMD packings, but also simultaneously allows for this high precision arithmetic without having super large noise growth. So in our example, we have this plain text space, which is an extension field of this Goldilocks prime, and the size of the vectors is 256. We found that this is optimal for our parameters. So how do we modify the HIOP to be as compatible as possible for homomorphic evaluation? This is generally a trade-off between the number of operations you have to perform, which you, of course, try to minimize, but then also the noise depth that they cause, because if there is the circuit you're evaluating is too deep, then you have to choose a large ciphertext space parameters, and everything gets less efficient, right? So as an example, take these FFTs, and so we use fractal, and you have to encode into Reed-Solomon codes, so you have to do some kind of FFTs, which is what normally is done in the plain text space. So to minimize the amount of operations you have to perform, you just use these standard FFT algorithms. You take an inverse and then a normal NTT. But of course, this has a large depth of the circuit. So on the other hand of the trade-off, you could see that, well, these NTT operations are just linear transformations, so we could compute them as a matrix vector product. But of course, this has a large amount of operations in general, and so again, you have bad efficiency. So you want to have a trade-off, an in-between trade-off. So one naive approach might be to take the normal NTT and then squash a few of the layers together and then compute them as a matrix vector product. But this is not very compatible with this SIMD packing that you have in the FHE scheme, right? As you may know, like in FFTs, in these butterfly algorithms, if you start from a vector, your end vector will be a bit reversed version of that. And so all the elements in our slot would have been thrown around, and it's very expensive in FHE to actually reverse this permutation. So we propose another solution, which is kind of to use a two-dimensional version of the NTT. So you represent the initial vector that you're performing the NTT on as a matrix. And as you can see, where the slots are aligned as rows, for example. And then you perform one NTT in each dimension, and one will be orthogonal to the packing, and one will be parallel to the packing. So the one parallel to the packing, there you really have to use the matrix vector products to prove that part of the NTT. But in the one orthogonal to it, it doesn't matter, because those you can just permute around easily, and there you can use the FFT. And we found that this was the best solution. So with some other modifications and choosing correct parameters, we make an example estimate. So for example, for fractal in an R1CS constraint system with 2 to the 20 constraints, we estimate, or we compute exactly like the amount of operations you need to do, and with what type of operations, and then what kind of noise growth they produce. And then using these numbers, we could make a micro benchmark of how long would it actually take to compute this thing using the timings of the GBFE scheme. And that turns out, if fully sequentially, you can do that in 9 hours. But of course, we specifically designed all these algorithms to be very parallel. So if you could assume a parallelization factor on a very performant server of 32, then you might be able to compute this in even 20 minutes. The reason we can't fully implement this is because the GBFE scheme is not yet implemented for non-power of 2 like atomics, which we have to use to get the Goldilocks plaintext space, but that is for future work. So lastly, this proof of decryption. It's very important that the proof of decryption is very cheap, because it's used in this private proof delegation application, right? So if the client who has to then make this proof of decryptions after the server homomorphically computes the proof, if that proof of decryption would be very expensive, then it kind of defeats the purpose of delegating the proof anyway, right? So we choose this sort of based on LNP 22, these Sigma protocols, because they can be more efficient. And then I'll skip over the math here. And then because we have to prove this bound on a linear operation for the decryption of the FHE scheme, we have to translate that into vector operations to be compatible with the proof. Also, these lattice-based Sigma protocols, they need special moduli so that you actually have a large enough invertible challenge space. So we have to mod switch down to this modulus at the end of the FHE operations. And then, of course, because we can only prove L2 norms, we'll have a slight relaxation factor, and this will just translate into an amount of bits, in this case 31 bits, you need to leave free of noise room at the end, which increases the ciphertext size, of course, that you have to commit to. So if you implement this with naive batching, because of course we have to provide a proof of decryption of many values, of many openings in Fry, you see the performance is like this. So for one proof of decryption, it's fairly efficient, but it scales very badly when it's increased. So we introduce a new protocol for batching many proofs of decryption by standard zero knowledge trick, which is just to take linear combinations, and then by the homomorphic property of the FHE scheme, well, you can make use of that to only do one proof of decryption. Hey, yeah, I need to wrap up here. And this, of course, has a cost of some additional bits of noise. But then it's important, then you can actually, the entire proof of decryption will only take approximately this linear combination, and then also one proof of decryption, which results in only less than 2 seconds in one thread and 1 second for 8 threads, and the proof size is fairly small and definitely negligible with respect to all the ciphertext you have to share anyway. We implemented this in C and it's built on this new laser library. So thank you. These are some references, and then I think we still have enough time for some questions.
Thank you very much. Right on time. We have some time for questions.
So if you think of the proof as authentication, you're authenticating, so your VFHE was encrypt and MAC, because the MAC, the authentication is on the ciphertext, whereas this is, you've encrypted the MAC, so this is like MAC then encrypt, in some sense.
I see the analogy, yeah.
Yeah, okay, so there's a vague analogy there. So usually we say one is better than the other. And so are there any kind of like separations of tax, or if you kind of take that analogy better?
Yeah, that's important to realize. So VFHE is a stronger security notion, of course. You can use VFHE to achieve these CCA-like security notions, but for simply this application, where there's just one round of interaction, you can always resample your secret key, right? So you want to encrypt your inputs, so you just sample the secret key, send over some ciphertext, and then you never have to use that secret key again. In these situations, blind SNARKs are sufficient, and they might be usable because their performance is a lot better than VFHE, of course.
Any other questions? I have one small one. To what extent can you achieve some form of like function privacy?
Yeah, this is not really, especially this instantiation, not compatible with function privacy, especially because the SNARK we are using is pre-processing, of course. But yeah, in general, this might be for future work. I don't know how compatible it is. Yeah.
Thank you. Let's thank the speaker once more time. We're going to hear from Stefanos now. Wait 1 second. This is good.